Okay, so let's get started then. Welcome everyone to the One World of Mathematics of Information, Data and Signals seminar. As a reminder, if you would like to pose a question either during the talk or at the end of the seminar, please use the Q&A feature. I or another organizer will then pose your question to the speaker. And today we are very pleased to have Stéphane Mallat as our speaker. Stéphane is professor and chair of data sciences at the Collège de France. He is distinguished research scientist at the Flatiron Institute, and he's also a professor of computer science at the École Normale Supérieure in Paris, where he is the scientific leader of the data team, which I will just add is my former lab and a place I always remember fondly. Stéphane has done fundamental work in wavelet theory, signal processing, machine learning, and high-dimensional data analysis, making significant impacts in, for example, image processing, auditory signal analysis, and physics, with over 100,000 citations according to Google Scholar. For his work, Stéphane has received numerous prizes and recognitions, including he is a member of the French Academy of Sciences. He's also a fellow of both the IEEE and the European Association for Signal Processing. He was a plenary lecturer at the International Congress of Mathematicians in 1998, and he was awarded the 2007 EADS Grand Prize by the French Academy of Sciences and the 2013 Innovation Medal of the CNRS, among several other awards. The title of Stéphane's talk today is Descartes versus Bayes, Harmonic Analysis for High-Dimensional Learning in Deep Nets. Stéphane, welcome to the MINDS seminar. The virtual floor is now yours.
Thank you very much, Matt. And I'd like to thank the organizers for this great initiative to organize these web seminars for everybody and students. So what I'd like to do today is first to come back to very basic questions about high-dimensional learning, to try to define what are the mathematical questions and in what sense harmonic analysis is fundamental to try to answer these questions and the relation with deep nets. So that's a vast program. So high-dimensional learning, there's typically two types of problems, classification, with the well-known example of ImageNet, where you have these huge databases with thousands of class and millions of examples. So typically what you want in that case is to find a class Y of an image, and X, the data, is a very high-dimensional vector, an image of typically a million pixels. Other type of problems are regression problems. Here I'm giving the example of the estimation of the energy of a physical system whose state is specified again by a vector X in dimension D. And quantum chemistry is an example where X would be the position of atoms from which you would like to estimate the ground energy. So all these problems are in very high dimensional and are raising a lot of mathematical issues. And I'd like first to try to discuss a bit how to state these problems mathematically and what is the role of harmonic analysis to try to answer these problems. So there is a simple question I'd like us to think first is, do you think it's more difficult to estimate the answer Y from data X in dimension D when D increases, or is it easier to do it when D increases? Now, if you think at this problem from a deterministic, let's say, Cartesian point of view, where you view the answer Y as a function of X and you have examples X1, X2, and so on, it basically amounts to interpolate this function. So it's a function approximation problems. And since X is in dimension D, the number of such function will grow exponentially. So you have this famous curse of dimensionality. So in this deterministic framework, yes, clearly, the problem is more difficult when D increases. Now, of course, you can try to get solutions which are reasonable to this problem, basically by putting some prior information about the function f that you are trying to estimate so that you can indeed do the interpolation. And here we go into functional analysis. It's about trying to define sufficiently regular functional spaces. And the typical strategy to do such an approximation would be to build the approximation from a linear expansion within a dictionary or some kind of basis phi, hopefully sparse, so that you can estimate this expansion from the data. And a typical result of that type is the famous universal approximation theorem for one-layer networks. Now, if you think about this theorem, it is essentially saying a high-dimensional function can be expanded in Fourier in high dimension. There are, of course, very subtle refinement around that, but the core of this theorem is not much more than just saying Fourier expansions are complete. Now, what is interesting is that since 1992, I think that was about the time where these theorems were refined, there hasn't been much improvement about results on trying to define better functional spaces. And maybe the reason is that that's not the way one should ask the question. Another way, that's the natural way we ask the question as a community, let's say in functional analysis, signal processing, especially being French, where you have a tendency to be very deterministic. But you can view the problem differently, and you can view the problem from a probabilistic point of view. So from a probabilistic...
Oh, sorry, Stéphane, we have a quick question about the first column there, if you don't mind.
Yeah.
The question from the audience is, when you say more difficult, do you mean in the sense of recovering the exact function that the data follows, or in the sense of recovering any function that satisfies the observations?
I say it in the sense of approximating a function, and in the usual way people think by saying high-dimensional problem suffer the curse of dimensionality because there is a combinatorial explosion of possibilities. But obviously there are ways to go around that, and in some sense that's what we'll look at on the next column. Great. So on the next column, instead of viewing the problem from a deterministic point of view, let's look, and that's the classical thing that you do when you look at integral from a measure theory point of view. We fix the value y, and let's look at the set of x, which corresponds to a value y. In other words, we define the level sets of the function. And from these level sets, you can define a measure. The measure will correspond to the uniform measure on the level set, which will basically define for typical x the probability to encounter a given x, an x given the value of y. Now, if you think that way, you are immediately in the framework of Bayesian probabilities and Bayesian statistics. The Bayesian estimators for the problem will consist in trying to find the class y or the answer y, which will maximize the probability of y given x. And then if you apply a Bayes formula, you can relate that to the measure that you've defined on your level set through the prior p of y. Now, if you think in these terms, then if you increase the dimensionality of x, obviously, you are going to get more details about y, so it should be easier to get your estimation. So in that case, you would say, no, the problem is not more difficult, it's rather easier. And this is quite intuitive in the sense that if you have an image which is a low resolution image, a priori it should be more difficult to identify the object than if you have a very high resolution image of several thousand points. So what's the math which is behind that? The idea, if you put yourself in this framework of measure theory, is that what you are going to try to do is to find again a representation phi of x, which is going to concentrate each of the class in a different position of your, let's say, parameter space, or the space where phi of x lives. And if you can indeed do such a concentration and separation, you will be able to identify the class from where you are going to land for each of the x. So if you think in this way, what is phi of x? Phi of x is not anymore a dictionary or a basis. Basically, it's an empirical moment which is going to concentrate your data and concentrate it in separate places for different y. Now, this is obviously not about really thinking whether things are stochastic or not stochastic, but it's really about thinking at this problem in terms of measure theory. So that's usually the way engineers view the problem. And let me continue on that track to see how all this relates to harmonic analysis. Okay, so if we put ourselves in this framework of probability, the issue now is to find a function phi of x that is going to concentrate the values of your data x in RD, and the value should concentrate for a single x. In other words, whatever x which belongs to a class should concentrate close to the mean. Now, if you want to indeed have such a concentration result, what you need to do is, in some sense, use some kind of central limit results. So what you're going to do is you're going to try to average some weakly coupled random vectors that you can compute from x, which hopefully have the same distribution, which is a type of stationarity property. And you are going to compute your phi of x from this average, which hopefully, when the dimension increases, is going to concentrate very close to the mean. Now, of course, this mean, you also need to make sure that they are separated for the different y, which is what I was saying. So you also need to make sure that these different expected values are different, so that indeed you need to separate the different y. If you are in a situation where indeed you have a sufficient concentration, you can apply large deviation models, which basically are going to say that the log probability, or let's say the log likelihood of y given x, when you go far away, are essentially going to decay exponentially. So the log probability is going to be linear as a function of phi of x. So basically here, I'm just rephrasing some basic information theory point of view. If you take this point of view, the problem is not anymore to approximate a function, but to obtain these concentration results. And of course, the whole difficulty is to define these phi of x. And that's where harmonic analysis kicks in. Harmonic analysis is going to kick in. Why? Because we need some kind of stationarity in order to find the variables which you are going to average. In other words, some form of symmetries of the probability distribution relatively to translation, rotations, and Fourier transform is going to come in. You also need to build some weakly coupled variable so that the average does concentrate, and some kind of Markov dependence. So you need to separate the variables. And again, harmonic analysis provides you the tools to do so. Okay, so what's the relation with DeepNet? The relation with DeepNet is that these are incredible algorithms which are able to do such a concentration. You all know the architecture now of these algorithms. This is illustrated in the case of an image, where you have a succession of convolutions. So the linear operator here are spatial convolutions. They also recombine the information across channels in order to get the next value. And at the output, you apply a rectifier. In other words, the max of the value and 0, to which you may add a bias, in which case you subtract the bias before taking the max and 0. And you cascade these operators until the last layer. And typically now the last layer is 1 pixel wide. So you have many channels, but you've essentially completely lost the spatial variable. you obtain a low-dimensional vector where you have a strong concentration. There has been a lot of experiments showing that the classes get very separated in this vector, and you get a final linear combination with a softmax, if you do classification, to estimate your class. Good. One way to view this machine, once it has been optimized, for example, through gradient descent, stochastic gradient descent, is essentially a nonlinear harmonic analysis machine, which is able to take your input, concentrate, and separate the different class. And the $1 million question is, of course, how does it do it? So that's what I'm now going to try to look at. So for the overview of the talk, to try to understand the math and, again, why harmonic analysis is important to look at that, I'm first going to look at this problem without any learning. So suppose that I have to define by hand this phi of x from some prior information I have on symmetry, stationarity. How would I define it? And in order to tackle this problem, I'm going to look at a somewhat simpler problem, which is the problem of trying to define models of non-Gaussian processes from, again, a single realization. Now, these problems are not so easy. For example, you may want to model turbulence, and modeling turbulence is an open problem in physics for the last 60 years since the work of Kolmogorov, essentially. Now, why I'm going to begin with that? Because very naturally, we are going to arrive to statistical physics, which will specify the problem in mathematical terms. And that will lead us to harmonic analysis. What do we need to do in order to address these problems? And that's where wavelets will come in. That's where the rectifiers will appear as being very important. And there is two things that will appear behind rectifier. One is the notion of sparsity that we see all over many works, but I'd like also to insist on phase. I'd like to show that phase is very crucial to try to understand what's happening when you get very nonlinear. And then we'll look at the same approach, but for classification, and we'll see how it relates to multi-scale deep neural network. We'll look at, in particular, ImageNet. Now, of course, this is not going to solve a complex problem such as ImageNet. So the next part will be, okay, we need to learn, but what do we need to learn? And what I'm going to show is that what you essentially need to learn is along the channels. Convolution in spaces, you have enough information to specify them, and wavelets will be enough, even to get state-of-the-art results on ImageNet. Now, to understand what is learned is really a complicated problem. So there has been a lot of theory. What I'd like rather to emphasize is that we also need experimental setup to understand how to develop the math. And that's one point of view that I'll try to take today. Okay, so generative models. There are very nice results that have been obtained by, for example, Matthias Bege and his collaborators. So basically, what they did is use a network that was trained totally independently, for example, with ImageNet data. Then they take one realization of the random process they want to model, for example, one of these three. They decompose this one realization in their network and compute each of the layers. Now, for each of the layer, they compute the correlation statistics between any two elements at any two different channels. So that defines a big set of statistics that they average in space. And then from these statistics, they resynthesize new images. So how do they do it? They begin from Gaussian white noise, and they do a gradient descent in order to adjust the statistics of X, in other words, the correlation of their decomposition in the networks, so that it's nearly equal to the statistics of the original image. And by doing that, they recreate new, very nice looking images that looks like new realization of their stochastic process. So let me begin with this and show how you can get a statistical physics interpretation. And by going along this path, we'll see what are the harmonic analysis questions. Okay, from a statistical physics point of view, the key idea is that you're making observations. So phi of x now will be called an observation in statistical physics. And these observations concentrate at a macroscopic scale. In other words, phi of x is going to be very close to its expected value up to epsilon in probability. So what that means is that if you take any typical realization of your random process, it's going to be completely concentrated by this function phi of x. Now, let's pick one particular x0. This x0 is going to be mapped in this ball. So now what I can define is a microcanonical ensemble, which is a set of all x such that the observation phi of x is close to phi of x0 up to epsilon. Why? Because I know that any typical realization should satisfy this property. So that's my microcanonical ensemble. It's a set of all possible x that is going to be mapped in this ball. Now, that's the concentration side. But what I also need is that the microcanonical ensemble should not be too different from the typical realization. That's important if I want to separate a realization of my random process from any other image that I can encounter, okay? So I would like that this microcanonical ensemble not to be too large, so phi has to be rich enough, and that's where you get this idea of sufficient statistics. Good, so now you can define a microcanonical model. A microcanonical model is going to be a probability distribution which is going to have a maximum entropy conditioned to the fact that it's supported in this set. And because this set is bounded, it's going to be the uniform distribution in this set. So that's the model. And now you can create new images by sampling this microcanonical set. You can do that with metropolis Hastings algorithm or with a gradient descent on this energy as people do, which initialize with white noise, which is a kind of poor man metropolis Hastings algorithm, but much faster. Okay, so now how does it relate to models? Now, when you are in very large dimension, as I said, you are going to concentrate around the mean. So you can replace your microcanonical model by a macrocanonical model, which basically impose that the expected value of your probability distribution is equal to the true expected value. Because basically now you know nearly perfectly the expected value. And if you maximize the entropy, you get your Boltzmann Theorem, which says that the solution is going, if it exists, going to be a Gibbs distribution. Good. So now, what the Gibbs hypothesis basically is going to say, if you are in sufficiently high dimension, you aggregate near the mean. So the macrocanonical model that you can measure should converge to this Gibbs distribution. In other words, you get the kind of model you wanted. The log probability is going to be a linear function of your phi of x up to a constant. And there has been, of course, a lot of math to understand under which condition this is going to be true. That's related to large deviation theory, basically since the work of Varadhan in 1966. So this is a relatively mature mathematical field. What is not mature at all is to understand how to define this phi of x. Now, there is obviously one very simple case. Suppose that your random process is Gaussian and stationary. In that case, what you know is that the phi of x is supposed to measure the covariance. So you are going to compute the empirical covariance. And because you know that your random process is stationary, you are going to average it on translation. If you do so, you are going to get a Gibbs energy, which is basically the Gaussian model, which is a bilinear function of that quantity. So it's a Gaussian model. Good. So you can try that. So you have your P of X. Basically, what you are measuring is the covariance. So in some sense, the ellipse that includes the distribution. And that's the Gaussian model. So if you do that for a fluid, this is the Gaussian model that has exactly the same covariance. It's okay, but it's not great at all. This is a turbulent gas. This is the Gaussian model. It's not great at all. And obviously, the reason is you've essentially measured the principal axis of inertia, but the distribution of P of X can be very different with it. Now, how can you check that? Well, you can trace an axis W, project on W, compute the marginal. If you are truly Gaussian, then your distribution should be truly Gaussian. But if P of X is not at all Gaussian, if you look at the distribution along this axis, it may not be Gaussian at all. Okay, so that's what we need to discover. Now, again, why harmonic analysis? Because you are stationary, so what is the reference basis? It's the PCA basis, and obviously, it's going to be the Fourier transform. So, the first type of problem that we're going to face is to detect these non-Gaussianity phenomena. So, what does it mean if you have a 1D distribution? If you look at the marginal, this is a Gaussian distribution. You may have two kinds of phenomena. Either your distribution is very peaked, and that corresponds to sparse coefficients, or you may have a skewed distribution, more on the left than on the right, and that will correspond to a phase asymmetry. So we're going to see the two phenomena. What is important, and what I'm going to try to show, is that the ReLU linear rectifier unit is able to capture both phenomena and therefore able to capture this non-Gaussianity. The other thing that it's going to capture is the correlation between variables which appears to be non-correlated but which are very dependent. And again, phase is going to play an important role. Good, so the first step to do that is you need to find the direction in which you want to project X in order to get something which doesn't look Gaussian, hopefully. To do that, we have a tool, sparsify the signal, wavelets, scale separation. Okay, so let me be very brief on wavelets because suppose all of you know about it. So a wavelet is basically a localized sine wave. I consider it here as a complex form with the cosine in real part and sine in imaginary part. The wavelet is going to be dilated, so that's my dilation factor. And like a sine wave, all these wavelets are going to be rotated. So that's a rotation parameter. And a wavelet transform here is essentially just going to be a convolution of X with the wavelets, which is going to be centered at a certain frequency lambda. So if you look in the Fourier domain, because you have here a convolution, it's going to be a product. And the wavelet is basically a bandpass filter, which is well localized in Fourier. If you rotate the wavelet in space, you are going to rotate it in Fourier, the support. If you dilate it in space, you dilate it in Fourier as well. And you are going to cover your whole Fourier plane with all these filters. Now, there is one thing which is important to realize. Because the wavelets have nearly disjoint frequency support, a wavelet coefficient at one scale or angle is not correlated with any wavelet coefficient at another scale or another angle, just because Fourier is the PCA basis. Okay, so let's look at an example. This is an image. You compute the first layer of wavelet coefficient. Most coefficients are gray, few black and white coefficient of large amplitude, very sparse. Then you go to the next scale, very sparse also, next scale. But one thing that you begin to realize is that the structures look very much alike across scale. So it's very strange because things are totally non-correlated, but they are very dependent. Now, why are they non-correlated? It's because of the phase fluctuations, which creates this decorrelation. So one of the questions is how to capture this dependence across scale, which will be completely key to define the geometry of your structures. And that's where ReLU comes in. Okay, so that will be the only page of calculation. Let's take a wavelet, and because I want to apply a ReLU, I'm going to take a real wavelet. So my wavelet psi lambda was complex. If I multiply it with a phase term, I'm now going to get a wavelet which has a phase alpha. Now let me apply a linear rectifier. And what I want here to show is that basically the linear rectifier is going to transform the phase, not the modulus. Now why? I apply the rectifier on this quantity, which is the real part of X convolved with my complex wavelet up to the phase. Now, the complex wavelet transform, I can separate the modulus part and the phase part. Now, the ReLU, it's a homogeneous operator. If I multiply a number by alpha, if alpha is positive, I can get the alpha outside. In other words, if I take the ReLU here on this quantity, I can pick the modulus and put it outside the ReLU. What am I going to get? The thing that is going to get inside will only depend upon alpha and the phase, and you can basically show that it's going to be the ReLU of cosine alpha. So it's a new function h, and what is going to be this h? H is a window. It's a phase window that is going to select the phase between minus pi over 2 and pi over 2. Okay, now let me take this quantity and let me compute the Fourier transform relatively to the phase. Because here the phase of the wavelet transform was translated by alpha, you can verify in one line that the frequency index associated to alpha is going to be a harmonic index. It's basically going to take the phase of the wavelet transform and multiply it by k. You see, this looks almost like taking the wavelet coefficient to the power k. The only difference is that you don't touch the modulus, but the phase, you take it to the power k. I will write it that way. That's what I'll call phase harmonics. It's only the phase that changes. Now, one thing that you can verify easily from that, if you take the expected value, you'll basically, of the ReLU, you'll get the same thing that the expected value of the modulus. So you're going to kill all the phase phenomena. Now, one point, when I compute a Fourier transform along alpha, if you think of a network, I'm doing a linear transformation along the channels in order to produce these harmonics. Good, so let's now try to build an appropriate phi of x. I want to capture this dependence. So one way to do it is to build phi of x simply as the correlation matrix of the rectified wavelet coefficient. Now, if you do that, you are going to get a huge full matrix. If you compute the Fourier transform along the phase through this transformation along channels, you are going to get a correlation between the phase harmonics. And you can verify that these will almost always be zero unless the frequency lambda multiplied by the phase exponent is equal to this frequency lambda prime multiplied by k prime. In other words, you're going to get a correlation matrix which is now very sparse. Okay, what are you building? Let's look in the Fourier domain. Until now, all the coefficients were decorrelated within different frequency bands. Once you've put the ReLU and you looked at it from a harmonic point of view, you are creating correlation between different bands for each different pair of harmonics. And that looks like a Markov model that you are creating local dependence between the different frequency band. And I will only take k equals 0, 1, and 2. Okay, let's do it. And that's the work of Cixin Zhang on random processes. So you begin with your X, which are different examples coming from statistical physics. This is a gas turbulence coming from astrophysics. That's the model. I'm going to build my covariance matrix, but I have very few non-zero coefficients. So I'm going to have of the order of log d squared non-zero coefficient that I will need to compute, which are these ones. And from that, I'm going to get a Gibbs distribution. Now, this Gibbs distribution, I can sample it, and these are the samples that you are obtaining. Now, you see that as opposed to the Gaussian model, now you restore the geometry. Why? Because you've basically realigned the phases across different frequency bands. The other thing is, in the case of the deep nets, I forgot to mention it, but the number of moments, covariance moments that you get in these models of the order of 20,000, whereas here you only need 2,000 once you've understood the mathematics and you produce model of same quality. Okay, so that's to show that harmonic analysis will help us concentrate, find the right variables. Let's now move to classification. So, classification, the problem now is to try to find the probability of y given x. And as I said in these models, basically you want to find a phi of x such that you can derive this probability distribution just as a linear combination. That's the principle also of linear logistic regression. So you need a phi of x which is going to concentrate the value of phi of x, but in different regions for different y. Okay, so the first thing we're going to try is to do it without learning, and then we'll see where are the failures. So to do that, you need prior. The first prior is the problem usually are invariant by translation. So this probability distribution is essentially stationary. So you can try to build your phi of x by doing a spatial averaging in order to build concentration through averages of hopefully decorrelated variables across space. The second prior information is that when you have small deformations, these are examples in these videos, you see when the image is slightly deformed, essentially the objects, the paintings is essentially the same. So you want to make sure that small deformation preserve classes. In other words, preserve the concentration. So you need to make sure that phi of x is stable to small diffeomorphism. Last thing, of course, phi of x must separate to a class. But because we don't know at this stage anything about the class, the only strategy we can take is to gather as much information as we can through the phi of x. Okay, so we have two problems again. Build phi so that it concentrates, but also so that it separates the different classes. So we begin with our signal, I show it here in 1D, or our image x. First thing, we begin by averaging because we know that there is some stationarity or invariance by translation. If the invariance by translation is just local, we'll just do a local averaging of a certain scale here, 2 to the jx. Now, if you are globally invariant to translation, that's great because you can completely average, so you are going to concentrate much more. But obviously you have a problem, you have a problem which is going to be that you've lose much too much information, you've lost discrimination. Okay, where's the information you've lost? The information you've lost obviously is all the high frequency you eliminated, and this information, in order to preserve the separation, you can recover it through the wavelet coefficients. Now, these wavelet coefficients, you need again to concentrate it. So we are going to do the same thing that we did before. We are going to apply a rectifier, and then we are going to average it in order to get something which is locally or globally invariant. But where do we lose information? We lose information when we do the average. Losing information means that there is a risk that we won't be able anymore to separate classes. So let's try to recover the information. How? We need to recover the high frequencies that we've lost, and we do that with a new wavelet convolution to extract the high frequencies. Again, you want to build something which concentrates, so you are going to apply a rectifier and an average. And that's the principle of these scattering transform. So basically you do a wavelet transform and you apply a rectifier. And then each time you make the averaging and you extract the complementary information as wavelet coefficient. So you reapply a second wavelet transform, potentially a third one, and so on, until the points that you've put everything down so that you've averaged everything in order to get your concentration. Good. Now look, that begins to look a bit like a neural net. The only thing is, it's rather a tree. There is no communication here between the different channels. And there is no learning. And obviously, somewhere we are going to pay for that. But let's continue. The important property that results from the fact that we did this scale separation is the fact that we are stable to deformation. If you deform a signal, which is basically about doing a translation that depends upon space, this corresponds to the local dilation. And one thing that you can prove is that if you deform the signal and you compute the scattering coefficient, the distance to the original coefficient will be of the order of the size of the deformation. So basically, you have your stability. Now, that's going to be very important. Think of the scattering transform as a network, and the number of layers is the number of scale. This is the transform. So now you've reduced the resolution in space because you subsample by 2 to the j, and the channels corresponds to the different phase and frequency. Now, if you want to do a classification, you are going to apply a linear classifier, and you are going to get your y. So now you can apply that to examples. That was the work of Johan Bruna during his thesis. So simple problem such as MNIST. This is simple because essentially the main source of variable are translation and deformation. So that's ideal because we know from our priors this information. You apply a scattering classifier or a deep net, you get about the same thing. The number of scale here will be only 3 because the digits don't move so much. So it's really locally stationary. If you want to classify texture, you need to average much more. So you are going to do a global averaging to concentrate your random process. Same thing, you can get very good classification rate, and deep nets don't do any better. You can work on quantum chemistry. That was, in fact, the work of Matthew Hearn with many collaborators afterwards, Michael Heikenberg, Louis Thierry, George Cacharis. And what they basically prove is that you can do quantum chemistry from, and therefore regress the energy of these molecules directly from the scattering coefficient and get a precision which is of the same order again than DeepNet, and which is very good. But, there is a but, these only until now apply to small molecules because these are the only database we have. So it looks very much like a kind of MNIST problem of quantum chemistry. Now, when you move to a real big problem, ImageNet, things change completely. You now have 1,000 class, 1 million image to train. If you do DeepNet, AlexNet in 2012 got 20% error. If you do a scattering, the error is twice bigger. If you now do a residual network with 50 layers, you get even much better, 7%. So the question is, what is learned? Obviously, now you need to learn, but the question is, what do you need to learn? Okay, so the first idea that comes to mind is to say, okay, all this is about pattern recognition, isn't it? So maybe somewhere we do need to learn patterns. And what could we think in terms of mathematics? Well, pattern means that your X, you can expand it with a dictionary of different patterns in a very sparse way as a linear combinations of these patterns, okay? So basically, you can view this problem as a sparsity problem, and many authors thought that in these terms. So basically, you want to approximate X as your sparse vector multiplied by Z, but these dictionary coefficients may be very redundant, so Z is not D transform X. Okay, there is a kind of explaining away phenomena. If you choose one pattern, you are not going to choose a correlated one. How can you compute this Z? well, that's the classical sparse L1 expansion. Basically, you want to recover a close approximation of X, but you also want to have something which is sparse. And I'm going to impose that I have a positive code here. So you have one parameter. And this parameter is basically what is going to define the level of sparsity. You can view it as a kind of threshold on the coefficient of the dictionary. So you can solve that problem to find the optimal code with a convex minimization. And as most of you know, you do that with iterative proximal algorithm. Now, these iterative proximal algorithms, you can implement them in a deep net. And that was the work of John Zarka, Louis Thierry, and Thomas Engles. Oh, let me come back. So the idea is each iteration goes through applying a matrix which only depends upon D. And then, in that case, the proximal operator happens to be the linear rectifier. And you have a bias, and the bias will be threshold. And we're going to use a nomotopy algorithms where the threshold progressively increases until the final threshold. Okay, so once you've implemented that, you can try to learn the dictionary. What does it mean to learn the dictionary? That means that now you're going to look at that as a deep net, and you are going to optimize the matrix D in order to minimize the classification error with a training set. So you are going to minimize the loss, and the parameters are now the dictionary that you want to learn and the threshold. Now, how many layers do we need? In that case, about 12 layers, because you have a very fast decaying algorithms, which essentially gets you the sparse code within 12 iterations. And that's the whole work that they did. Okay, now let's look at the result. AlexNet, I said, 20% error. If you do a scattering transform alone, you get about 40% error. And here the classifier I'm going to use is a double layer classifier, which will be exactly the same than AlexNet. So same classifier, twice more error. Now, if you compute the scattering transform, but now along the channel, you compute a sparse representation of these channels with a dictionary that you learn in order to minimize the classification error. So now the output of that will be a representation which is very sparse, about 3% non-zero coefficient. The error drops to 18%. So that means that by learning a single matrix which sparsifies the problem, you go back to ImageNet, which learns all the layers. Question, why does it work so well? How come you have such a jump of 20%? And we tried for many years to get that by improving scattering transform, never worked. Suddenly you just learn one matrix on the channels which sparsify, it gets you a big improvement. Okay, the obvious hypothesis is that you need sparse dictionaries, which are basically selecting few discriminative patterns for classifying. Now, I would like to say that in this domain, it's very easy to make hypotheses and then write papers, but very often these hypotheses are wrong. And I think it's very important to set up having an experimental setup which allows us to verify whether these hypotheses are reasonable or not. One point of building this architecture was to try to simplify the whole problem so that we could test hypotheses. So the first thing we did was to test this hypothesis. Now, how can you test it? Let's get the sparse code, and let's reconstruct from the sparse code. So that's going to be an approximation of the input. It's not sparse at all. And now you've completely lost all the sparsity information, and let's classify from that. And surprise, you essentially get the same performance. So what does that mean? No, it's not sparsity which was the source of improvement. Second observation, if we now look at the reconstruction, which is supposed to be a sparse approximation of this, we look at the error, the relative error is of the order of 50%, so it's very big. Now, why is that so? Because if you look at the bias which was learned, it's very large. So basically, you remove a lot of information. Okay, so the immediate next hypothesis which comes to mind is basically saying maybe the dictionary is really removing non-informative noise, which helps the concentration by using a large bias and this explaining away mechanism. So now let's test that. How can we test whether the explaining away mechanism of sparse coding is useful? We are going to replace the 12-layer sparse coding by one layer, simply applying a matrix D transpose and the ReLU. So it's a linear transform, which is thresholded, essentially. You are going to get a sparse set of coefficients if the threshold is large, and then you do the classification. And that's the work of John Zarka. And big surprise, you don't lose anything. In fact, he even improved the result. What does that mean? We don't need sparse coding. No explaining away is needed. And the explaining away phenomena, because of redundancy, is what is hard. You can just apply a single matrix and a ReLU. Now the question is the threshold important? A priori, you think yes, if you need to remove noise. So what John did is take this threshold and set it nearly to 0, so that Z is not sparse anymore. And the error is a little bit worse, but almost not. So basically you preserve. What that means, no, it's not an issue of thresholding and getting something sparse. However, there is one thing you cannot remove, is the rectifier. If you remove the rectifier, everything gets equivalent to a linear transform, and you go back to an error of 40%. Okay, so the question is, what is this rectifier doing here? Okay, rectifiers. We saw that basically the rectifier has two kinds of roles. The rectifier separates the modulus from the phase, and then you can, in the different channels, process one or the other. So question, this rectifier, is it really the phase, or is it the modulus of information, which is important for the classification? A priori, I was absolutely sure that it was the modulus. Why? Because when you apply it on a wavelet coefficients, the main component is really the modulus. Okay, so we tested it, or rather John Zarka tested it, by replacing the rectifier by something that eliminates all the amplitude. You just replace the rectifier by a sine function. So the output will be either 1 or -1. So you just have a phase information. Okay, so let me remind you. If you do a simple scattering transform on your J layers and a linear, here I'm going to use a linear classifier. You are going here with a linear classifier, the error is bigger than with this double layer classifier, 55% error. If you put this one layer with a ReLU, the error is divided by 2, you get an error of about 27%. What if you replace the ReLU by a sine? And the big surprise that you basically, with the same dictionary, we don't even retrain the dictionary, essentially get the same error. And you can get a little bit better if you retrain the dictionary. So what that shows is that across channel, it seems that it's the phase, the alignment of the phase, the asymmetry, which is playing at least a very important role. And why can now the phase play an important role? Because before you did the spatial convolution and the rectification, which basically realigns the phase, at least it's a hypothesis. And of course, if you only work with the phase, that means you kill all the amplitude variability, and you therefore improve concentration. Last question. Okay, in all these results, we are still quite far from a residual network, which does much better. Not only that, but the final classifier is this double layer classifier that ImageNet was using. Is it possible to basically get close to a ResNet? And again, that's the work of John Zarka. So the idea is the following. until now, we've cascaded the wavelet transform ReLU one after the other. That was the scattering transform. And then we did the filtering across the different channels. Let's do in some sense like a deep net. We first do a wavelet transform and a ReLU, but wavelet is not learned. And now we learn a convolution operator along channel, but it's a 1-1 operator, no spatial information, just a recombination of along the channel. And then we reapply in space the wavelet transform rectifier, and then we recombine the channel. It's a 1-1 convolutional operator, and so on, until the last layer, and then we just do a softmax, and we get the result. And of course, here you learn each of the recombinations across the channel. In this algorithm, you've completely killed the spatial variables, so you need about 6 layers to do so. If you do that, you get 12% error on ImageNet. If you think of ResNet with 18 layers, you have 11% error. So it's about the same. Of course, if you increase much more the number of layers, which ResNet can do, 50 layers, you can go much lower, like 7% error. Okay, so what does that show? First of all, yes, you can recover performance of the order of ResNet without learning anything in space, just wavelet coefficients, with a number of layers which is not so large, only 6, and learning along the channel is the key element. Now the question, of course, is what is the nature of this learning? And what looks like is that the phase is playing a fundamental role following the previous experiments. Okay, so let me conclude on all this. The first point I'd like to come back to is the story of Bayes versus deterministic versus probabilist. And essentially, I've completely switched my gears. Until very recently, I was viewing this problem as a functional analysis problem, and therefore asked the question, what is the regularity of the function? What is the functional class? I think that's the wrong way now to view the problem. Of course, I may still be wrong, but I think of it very strongly. Now, I think if you look at the algorithms, if you look at what has been happening in functional analysis, basically there has been almost no improvement. And I think that the reason why there has been no improvement on the math of functional analysis in a high dimension is because it's the wrong way to look at the problem. The right way, I believe, to look at the problem is the way engineers look at it. It is about probability. It is about concentration and making sure that you have probability measures that separate rather than trying to find esoteric functional spaces. Now, that doesn't mean, again, that functional analysis is not important, and in particular, harmonic analysis. And that's basically what I tried to show during that talk. Harmonic analysis is one very important, if not the tool, in order to build these operators that are going to concentrate. And the reason is that you have invariants over groups. Because you have invariants over groups, you have the Fourier transform coming in, and here you are in the world of harmonic analysis. The other point, phase. Now, in harmonic analysis, if you think of it, most harmonic analysis until, let's say, the years 2000 was very much linear. And if you think at all the algorithms that were developed with thresholding, with de Novo denoising, and so on, all this is based on amplitude. People had a tendency to try to forget about phase because phase was viewed as a very complex, unstable tool. What basically I'm trying here to say, and that's a very natural idea, in fact, for physicists. Phase is very important, and phase is the object that you need to look at if you want to understand what's happening across frequencies, across scales, because that's what is going to realign things. Across frequency, across scale, that means across channels in a deep net. In other words, phase is going to be very important to recombine channels. Other elements basically, in this deep net, the main issue is understanding the channel interaction. Spatial variable, you can just do it with wavelets. That will be enough to build your multi-scale pyramid. So that's not the problem. Learning across channel, obviously, is very important. So I showed it for ImageNet. Otherwise, you get very poor result. But basically, we don't really know at that point, and probably it will take some time, at least it's a beautiful problem, how these learned operators are performing this concentration and separation. Now, I think this is a difficult problem. It's a difficult problem, and when we are facing such difficult problem, it's useful to do experimentation. And that's why I would like to come back to this idea of building controlled experiments for mathematics. The goal here is not to obtain very good classification result, but be able to change one module or the other. And that kind of approach that Jan Zarka has been working on seems to be very fruitful to try to eliminate at least bad ideas. Getting good ideas is, of course, much more difficult. So that's about it. There's two papers which summarize some ideas that I've been speaking about. And I'll be very happy to answer questions if there is any. Thanks.
All right. Thank you, Stéphane, for a really excellent talk and a very stimulating set of questions here. So indeed, we can now open the floor for questions. Panelists, of course, you may unmute yourself and answer or ask your question directly. And audience members, you may ask a question through the Q&A functionality. There is one question in the Q&A already, so I'll start with that one from the audience. The question, Stéphane, is the following. What could be the cause of the brittleness of deep learning algorithms from the perspective that you've sort of presented here?
The cause of the?
Brittleness. So, so basically, they're not robust, say, to the lack of robustness. Exactly.
Oh, the lack of robustness. In that framework, that would be the learned operator across the channels. There is no control on their norm. And because you cascade them, at least in what we did, because you can cascade them, a small modification of X can lead to a large transform. The wavelet transform is and rectifier is contracted. So what you do in space is okay. The problem is what you do across channel. You need to have good classification performance, but in order to be robust, you would need to control the norm of these operators. And that we didn't do, and there are issues around that.
Great, thank you. Let's see, we have another question here from the audience. The question is the following. How do you think the connection between concentration and separation, or I guess, what do you think of the connection between, on the one hand, concentration and separation, and on the other hand, the balance from information bottleneck type analysis?
Oof, that I wouldn't know. That I don't know. It's interesting. I don't know. The concentration, separation, these are the two opposite notions, because obviously concentration is easy to get. You just average everything and you concentrate, but you've lost everything. So that's what gets you your balance. It's a good question. I would need to think about that. Okay,
great. We have another question from the audience. Essentially, what about graph-based learning, geometric deep learning on graphs? Say, how might we apply or test the phase hypothesis in that setting, where I suppose behind this question is the idea of doing harmonic analysis on graphs, right?
Okay, so in the case, in order to access to the phase, really, you need to go complex, because of course the phase, I mean, you can transform the ReLU in a 1 minus 1 and kill the modulus, and then you get the phase. But that's very brutal, and you may kill everything. If you want to simultaneously get the modulus and a phase, you need to be in a complex framework. Now, the question would be, can we compute complex wavelets over a graph? And I would think you can if you think of it as a manifold, but I'm not sure how much work has been done on that. But essentially, for the rest, everything is the same. Once you have a complex wavelet transform on your graph, then essentially everything goes through. And in fact, Matthew did a lot of work with Givolf on building on graphs wavelet transform to define scattering transforms. Now, but I don't know if your wavelet transform were real or complex.
They're real valued. I think actually, not to go too far off on our own tangent, but I think actually Edouard has recently started thinking about complex valued harmonic analysis on graphs. And, but yeah, so far this stuff with Guy has been real valued. Let's see, we have some more questions from the audience. Great talk, thank you. I'm wondering, how does your insight about phase can be viewed from the perspective of the previous talk by Richard Branuik? I'm not sure if you saw that one, Stéphane, but in other words, i.e. sine function instead of ReLU from the convex optimization point of view.
Now, as much, I haven't seen the web version of his talk, but I've seen several versions in a direct form. And as much as I remember, he's really building an approximation of the underlying function from these piecewise linear approximations. And the point of view is therefore really very different, because here the phase is used as a way to rebuild linear correlations between things which are decorrelated, to realign them. I don't see, it would be in fact interesting to try to build the bridge with functional analysis. But frankly, I had a very hard time, because the notion of concentration is not present in functional analysis. There is not this idea of independence. In order to build it, you would need to build some separation. So the short answer is, I don't see the direct link, but if there is one, it would be interesting.
Okay, great, thank you. Let's see, another question from the audience. Could the lack of robustness be explained in the Bayesian perspective from the fact that posteriors are not robust to the choice of priors?
I don't use any priors here besides invariance to translation and stability to diffeomorphism, which is used through the use of theta. So through the use of wavelets. So there is no, I mean, the prior normally is the probability of Y, but if you think, for example, of ImageNet, each class has the same probability distribution. The P of Y are uniform. So there is really no issue here of priors. So I don't think it's related to that, to the error on the prior, on that kind of models.
Okay, thanks. Let's see, from the panelists, were there other questions that were coming up?
I have a quick question. First of all, thanks, Stéphane, for the great talk. I wanted to ask, since the number of parameters you learn is much smaller, I'm not sure if you understand how much smaller, but it seems much smaller than a normal network. Is there any more inherent stability in the sense that maybe if you change the data slightly, the things learned might be stable in some form, and if you have two data sets, can you use the learned parameters on one to do better on another?
We didn't try. It's a good question. We didn't try. it would be worse because it's a way to investigate these operators across channels, to control them and so on. So frankly, I don't know. I would have a tendency, you see, I would have a tendency to think that it's simpler to work in this framework because again, in this framework, basically we are just learning the filters across the channels. And by learning the filters across the, so we don't have to deal anymore essentially mostly with the spatial convolutions because they are basically wavelets. So that's why I think it would be simpler, but still you still need to analyze these learned operators.
What is the order of magnitude of the number of parameters you learned compared with the size of the data? This wasn't clear to me.
We don't reduce the number of parameters as much as I know. I don't have the numbers in the case of AlexNet, in the final configuration, we had about the same or a bit less parameters. We only have one matrix D, but this matrix D is quite large. So it's not about reducing the number of parameters. We could try to reduce, but that was not so much the point. The point was to say, let's have just one matrix and analyze it. So the work hasn't been done on trying to compress.
Thank you.
I see a few questions from the audience. Here's another question, Stéphane. Do you think there is a relation with reassignment, which uses phase to sparsify the representation?
You mean of reassignment in the like Flandrin time frequency reassignment techniques? That's what the person's thinking about.
I guess I'm not sure, but
I wouldn't think. In that framework, reassignment was in order indeed to get better concentrated Vigneville type distribution. Again, here, phase is, okay, let me explain it from a physics point of view. Take a chord that vibrates, okay, like in a guitar. Because it's a physical oscillations, if you look at the different frequencies, they are going to go through zeros at the same points because the two ends of the chords are tight. What does that mean? That means that all the phases across frequency are aligned. So whenever you have take a Dirac, why when you reconstruct from a Fourier transform, which is flat, you get a Dirac? Because all the phases are aligned. If you disalign, then you get white noise. So alignment of phase is what differentiates something which is structured from something which is not structured. With the same amplitude, you can get totally different things, Dirac or white noise. So it is important in that sense. Now, of course, with wavelet, you can localize the information and go a little bit around, but not completely. So it's very physical. That's why I was saying the idea of phase, when you speak to physicists, they tell you, obviously you need phase. It's just that we got rid of it, mostly.
Great, thank you. Holger, did you want to ask your question?
Yes, hi, Stéphane. So I would like to go back to the question on robustness. So my question is, could you, when learning these dictionaries across channels, basically impose a constraint on the norm so that overall you get something which is robust?
Yes, that would be very interesting to try. You see, all these results are of John Zark are very new. So there is no maturity, and I hope we have no mistakes either. But he's very reliable, so it shouldn't be. But yes, it would be interesting to constrain the norm of these operators, which can be done through SVDs. and see whether we can still learn and stabilize the problem. Absolutely.
But did you check on the norms of these operators that you get?
Well, the problems is outside, these are the details here. There are renormalization. Each time we get out, we renormalize. So there is the norm of the operator, but there is also the renormalization factor. And renormalization is very important. So why do you need to renormalize each of the channel? In some sense, if you renormalize, that means that you realign the variance and you have again something that looks like something stationary. So you have this mix. So we didn't look at separately the norm, the renormalization factor, the products to see what's happening. But I suspect that the condition number is pretty bad because of the renormalization coefficients.
Okay. Yeah, okay. But there's something to do. Yeah.
Yeah.
Thanks.
Let's see. Any other questions from our panel or the audience before we go? Okay. Looks like that's it on the questions then, Stéphane. So,
Well, thank you very much.
Yes, thank you. Let me thank you once again for a really nice talk. And yes, we can give a sort of virtual applause. And yeah, for the audience, of course, we hope to see you all again next week. And yeah, that's it for today. So
okay, bye.
Bye.